For centuries, one of the biggest head scratchers in all of physics was about something we see every single day, light. Yeah, seems simple enough, right? But believe me, the deeper scientists dug, the weirder it got. So, let's jump right in. This right here, this was the central mystery. Is light a wave or is it a particle? Seems like an easy question, doesn't it? But the answer would totally flip our understanding of the universe on its head and kickstart a revolution in physics. So, what is it?
Okay, so to really get why this was such a huge deal, we've got to take a trip back in time. Let's go to the 19th century, when physicists were, pretty confident they had the universe all figured out. And in their rulebook, one thing was crystal clear. Light was a wave. Period.
And look, they had some really good reasons to believe this. I mean, brilliant minds like Thomas Young were running these amazing experiments. And they showed that light does all this wave-like stuff. It diffracts, it interferes. Things that back then you only saw in waves. It spreads out, it bends around corners, it makes patterns exactly like ripples on a pond. Okay, now look at this pattern right here. You see those bright and dark stripes? That's what happens when waves add up in some spots and, well, cancel each other out in others. It's exactly like when two sets of ripples cross on a pond. Now, a stream of tiny particles, like little bullets, they just can't do that. There's no way. So for everyone at the time, the case was closed. Light is a wave, end of story. Or was it? And then everything changed. Right at the turn of the 20th century, physicists stumbled onto this one simple experiment. But the results? They made absolutely no sense. It was called the photoelectric effect. And this little puzzle? It was the loose thread that was about to unravel everything they thought they knew. So the setup is super basic. You shine a light on a piece of metal, and if the light is the right kind, bam, it knocks electrons loose. You can kind of think of it like a cue ball smacking into a rack of billiard balls. Simple, right? But what actually happened was just bizarre. Okay, so this is where the old school wave theory just completely breaks down. Let's stick with an analogy. Think of ocean waves. A bigger, brighter wave should have more energy, right? It should hit harder. So a brighter light, a more intense wave, should shoot those electrons out with way more energy, make them go faster. But that's not what happened. Not at all. A brighter light just knocked out more electrons. They weren't any faster. The only thing that changed how fast the electrons flew off was the light's frequency. Basically, its color. And the clues just kept getting weirder and weirder. Get this, a really dim ultraviolet light, which has a high frequency, could pop electrons out instantly. But then you could take this incredibly bright, intense red light, which has a low frequency, and you could blast that metal for hours, and nothing. Not a single electron would budge. It's like the light needed a secret password, a specific threshold frequency to get the job done. And it was always instantaneous. There was no delay, no charging up like wave theory predicted. Physics was just broken. So this whole mystery needed a hero, a new detective with a totally radical idea. And in 1905, building on the work of another genius, Max Planck, a young patent clerk named Albert Einstein steps onto the scene. And he proposes a solution that was, well, it was as brilliant as it was completely out there. So the story really starts a few years earlier, in 1900. A physicist named Max Planck throws out this wild idea that maybe, just maybe, energy isn't some smooth, continuous river. Maybe it comes in tiny, discrete packets he called quanta. Now, most people thought, it's just a weird math trick. But Einstein, he took it seriously. He thought, what if it's not a trick? What if light itself is made of these little packets of energy? He gave them a name, photons. His argument was that light isn't a continuous wave at all. It's more like a machine gun, firing tiny, tiny bullets of energy. Each one of those bullets, each photon, is its own little self-contained packet of energy. And this is the heart of it, boiled down to one of the most famous equations in physics. E equals hf. All it really means is that the energy of one photon, that's the E, has nothing to do with brightness. It's directly connected to its frequency, the F. So, high-frequency light like UV, that's made of powerful, high-energy photons. Low-frequency light like red, that's made of weaker, low-energy photons. Simple as that. And you know what? The actual experimental data, it lined up perfectly. This graph right here, this is the smoking gun. It shows a perfect straight-line relationship. The higher the frequency, the higher the electron's energy. And see how the line doesn't even start until a certain point? That's the threshold frequency. It was exactly what Einstein's photon model predicted. This wasn't some lucky guess. This was proof.
So here's the solution to the whole puzzle. It's a one-to-one deal. One photon hits one electron. A single UV photon has enough punch in its little packet to free an electron. Instantly. It doesn't matter how few of them there are. But a red light photon is just too weak. You can throw a billion of them in an electron, but it's like trying to knock down a brick wall by throwing tennis balls at it. It's just never gonna work. Einstein had solved it. Case closed.
But you know how these stories go. In solving one massive mystery, Einstein accidentally opened a door to an even deeper, even stranger one. Okay, great. Light is a particle, a photon. But what about all that rock-solid evidence that said it was a wave?
Yeah, exactly. How could a stream of what are basically tiny bullets create that beautiful wave pattern we saw at the beginning? You know, the one with the bright and dark bands? Particles don't interfere with each other like that. They don't cancel each other out. Suddenly we have a whole new paradox on our hands.
And just when you think reality can't possibly get any stranger, it does. Oh, it does. So scientists decide to run the same experiment, but this time, instead of light, they use a beam of electrons. You know, electrons. Things we all knew for a fact were tiny, solid particles. And what happened? I'm not kidding. They got the exact same kind of interference pattern. The particles were acting like waves. This was mind-blowing. It led a physicist named Louis de Broglie to propose one of the most profound ideas in the history of science. What if everything, and I mean everything, has both a wave side and a particle side? What if every single moving object, from an electron to a baseball to you and me, has a wavelength associated with it? This whole wave-particle duality thing, it wasn't just a weird quirk of light. It was a fundamental rule of the entire universe.
So this whole incredible journey, which started with what seemed like a simple question about light, ended up forcing physicists to literally tear up the old rulebook. They had to write a brand new one from scratch, the strange, counterintuitive, and absolutely wonderful rules of quantum mechanics.
So, what are the rules in this new reality? Well, for starters, energy isn't smooth. It's quantized. It comes in these little packets. And two, light, and get this, everything else exists in this bizarre limbo state of being both a wave and a particle at the exact same time. Which one you see just depends on what kind of experiment you decide to run. Which brings us all the way back to where we started. So, is light a wave or a particle? The only answer quantum mechanics gives us is yes, it's both. It's neither. It's something so fundamentally weird and new that we don't even have words or analogies for it in our normal everyday lives. And that is the absolutely mind-bending thought I want to leave you with. This isn't just some weird trivia for physicists. This is a deep truth about the very fabric of existence. Think about it. If the fundamental building blocks of our entire world can be two completely contradictory things at the very same time, what does that really say about the nature of reality itself?